Hello friends, this is Pat Thakkar and in our today's lecture, we are going to solve numerical which is based on radiation. In our previous lectures, we have studied some basic laws related to radiation, how radiation through heat transfer occurs between the two systems. We have learned Kirchhoff's law, Stephen-Boltzmann law, Planck's law and Wein's displacement laws. And with the help of that laws, we have derived some equations. So, in our today's lecture, we are going to solve some numerical by using that equations. So before starting solving numerical, let's take a look on that equations which we have derived in our previous lectures. First, from the Stephen-Boltzmann law, we have derived equation for the black body emission power, which is given by sigma a t raised to 4, where sigma is a Stephen-Boltzmann constant whose value is 5.67 into 10 raised to minus 8. T is a surface temperature of the black body and A is area. EB is black body emissive power. The next equation is for the real body. Emissive power for the real body can be calculated by using epsilon, which is emissivity, into sigma into area into T raised to 4. Here emissivity of any real body, we have learned in our previous videos that emissivity of any body can be calculated by emissive power of that body divided by emissive power of black body at the same temperature. So the ratio of emissive power of the real body divided by emissive power of the black body at the same temperature gives the value of emissivity for that body. The next equation is for the intensity. This is the equation which we have derived, and the relation, this equation shows the relation between intensity and the black body emissive power. So this is black body emissivity IBN is equal to EB divided by pi. The next equation is for the wavelength of the maximum monochromatic emissive power, which is also known as the Wein's displacement law, which is lambda maximum into T is equal to 2898 mu m into K. The equation is derived by differentiating the Planck's equations. So here, what is the Planck's equation for the monochromatic emissive power? Emissive power for the particular wavelength. Remember, whenever object is above absolute zero temperature, it emits electromagnetic wave of different wavelength. So if we consider all the range of wavelength for the electromagnetic wave, it gives total emissive power. But for practical purpose, we are sometimes more interested for a particular wavelength of emissive or electromagnetic wave. So for particular wavelength, the emissive power can be calculated by Planck's equation, which is E lambda by B, which shows the emissive power of particular wavelength. This lambda shows emissive power of particular wavelength is equal to C1 lambda raised to minus 5 upon exponential of C2 divided by lambda t minus 1. Here C1 and C2 are the constants. If we differentiate this equation with respect to lambda, with respect to wavelength, then we will get this equation which is known as the Wein's displacement law or Wein's displacement equation. The last equation is for the maximum monochromatic emissive power. By the combination of Planck's law, by the combination of this Planck's equation and the Wein's displacement equation, the equation for the maximum monochromatic emissive power can be generated is equal to E lambda B is equal to 1.285 into 10 raised to minus 5 T raised to 5. Here T is the temperature. If we put a value of the temperature of the body in this equation, we will get the maximum monochromatic emissive power for that particular temperature. So these are the basic 6 equations which we have already studied in our previous videos. These are the basic laws of the radiation. Now, by using this equation, by using these relations, we are going to solve numerical which is based on radiation. So let's start with the first numerical. Effective temperature of body having area 0.12 meter square is 527 degrees Celsius. Here area of the body and the temperature of the body is given. We have to calculate following. First, rate of radiation energy emission. Second, intensity of normal radiation. And the third, wavelength of maximum monochromatic emissive power. So we know the equations for all of these three. So by using that equation, we will find out first rate of radiation of energy emission. In given data, we have area which is 0.12 meters square and the temperature of the body is 527 degrees Celsius. To convert it into Kelvin, we are going to add plus 273. So finally it is 800 Kelvin. So rate of radiation energy can be easily calculated by Stephen Boltzmann equation, which is sigma area T raised to 4. Value of sigma Stephen Boltzmann constant is 5.67 into 10 raised to minus 8. Area is given in question 0.12, and temperature of the body, remember you have to put temperature in Kelvin, so 800 Kelvin raised to 4. So by calculating these values, we will get radiation energy emission. Rate of energy emission is 2786.9 watt. This watt joule per second represent the rate of radiation emission at 800 Kelvin. Clear? Second, we need to find out intensity of normal radiation. We have relation of intensity and emissive power, which is IBN is equal to EB divided by pi. But here in this equation, we have to put EB in a watt per meter square Kelvin raised to 4. So for the watt per meter square Kelvin raised to 4, EB is sigma into T raised to 4. We know the value of temperature 800, sigma is 5.67 into 10 raised to minus 8 divided by 5. By calculating these values, we will get intensity 7392.5 watt per meter square. If you multiply here by area, then meter square will be cancelled. Okay, the last thing which we need to find out is maximum monochromatic emissive power, wavelength of maximum monochromatic emissive power. So if we want to find out wavelength for the maximum monochromatic emissive power, then we have equation given by Wein's, which is lambda max into T is 2898. The value of T is 800. So by putting value of temperature, we will get maximum wavelength for this maximum monochromatic emissive power, which is 3.622 micron. So this is the equations which we are going to use to calculate all of these three things. Now moving towards the next question. The sun, here the sun emits maximum radiation at lambda is equal to 0.52 micron. This is wavelength which is given. Assuming sun to be a black body, we have to assume sun as a black body. Calculate the surface temperature of the sun and the total emissive power of the sun's surface at that temperature. Okay, first we need to find out the surface temperature of the sun when lambda is 0.52 micron. So we know the Wein's displacement law, lambda max into T is 2898 micron into Kelvin. So from this equation, lambda max, which is given because maximum radiation at lambda is equal to 0.52. So we have value of lambda max, which is 0.52. So by putting value of lambda in this equation, we will get value of temperature at this wavelength. Temperature for the electromagnetic wave of this wavelength is 5573 Kelvin. Okay. Now we have to calculate total emissive power of the sun's surface at that temperature. At that temperature means at this temperature 5573 Kelvin. So we have to calculate total emissive power of the sun's surface at 5573 Kelvin. So for the total emissive power, the equation is sigma T raised to 4. Value of sigma is 5.67 into 10 raised to minus 8. And the temperature, we have just calculated the value of the temperature 5573. So by calculating this value, we will get total emissive power as 5.4 into 10 raised to 7 watt per meter square. If you want to find out if we want to find out maximum monochromatic emissive power, then we have equation for the maximum monochromatic emissive power 1.285 into 10 raised to minus 5 into T raised to 5. So at this particular 0.52 micron wavelength, if we put value of temperature which we get for the 0.52 micron, the temperature 5573, we will get maximum monochromatic emissive power, which is 6.9 into 10 raised to 13 watt per meter square. If it is asked in question, then you need to calculate this. Moving towards the next question. A furnace emits the radiation at 2000 Kelvin. Okay, here the temperature is given. Treating it as a black body. Okay, calculate first monochromatic radiant flux density at 1 micron wavelength. So first we need to find out the monochromatic radiant flux density. It means we have to calculate this E lambda B, which is calculated by Planck's equation. Here C1 lambda raised to minus 5 exponential of C2 by lambda T minus 1. We know the value of C1 and C2 constant. Lambda is already given. We need to multiply by 10 raised to minus 6 to convert it into meter. So raised to minus 5 as it is. So by putting the value, here the temperature is given directly in Kelvin 2000. So by calculating these values, we will get value of monochromatic radiant flux density at particular this wavelength, which is 2.8 into 10 raised to 7 watt per meter square. Now second, wavelength at which maximum emission and corresponding radiant flux density. So for the maximum wavelength, maximum emission wavelength can be calculated by lambda max into T. We have relation 2.8 into 10 raised to 3. The temperature is 2000 Kelvin. So by putting the value of this T, we will get lambda max. Maximum wavelength at particular this temperature should be 1.4 into 10 raised to minus 6 meter. Now at this wavelength, if we calculate maximum radiant flux density, then we have relation 1.28 into 10 raised to minus 5 into temperature 2000, which is given in question. So at this temperature for wavelength of 1.4 into 10 raised to minus 6 meter, the maximum radiant flux density would be 4.11 into 10 raised to 11 watt per meter square. Now the last thing, total emissive power, which can be calculated by sigma B T raised to 4. Sigma is 5.67 into 10 raised to minus 8. And total emissive power means all the wavelength are considered. So temperature 2000 Kelvin, which is already given. So the total emissive power is 907200 watt per meter square. Okay. Moving towards the last numerical. A grey diffuse opaque surface with absorptivity of 0.8 is at 100 degrees Celsius and receive irradiation of 1000 watt per meter square. Now the question is, what is irradiation? If the surface area is 0.1 meter square. So there are two terms which we need to understand before solving this numerical. Irradiation and radiosity. Radiosity is the total amount of electromagnetic wave emitted by any body per unit time per unit area. Now when any surface or any body emit electromagnetic wave, there are two things of emission. First, electromagnetic wave emitted due to its own temperature plus some amount of electromagnetic wave which are coming from the surrounding and which is going to be reflected by the body because of its reflectivity. So the whatever amount of electromagnetic wave, or we can say that the radiation which is emitted by any body, contains two parts. First, due to its own temperature. Second, the surrounding electromagnetic wave which is going to be reflected by that body. So the combination of both of this is known as the radiosity, which is total electromagnetic wave, or we can say that the total radiation emitted by any body, which is denoted by J, capital J. Now what is irradiation? It is just opposite of radiosity. Irradiation means total radiation, or we can say that the total electromagnetic wave which are going to be incident on any body is known as the irradiation, which is denoted by capital G. Done? Clear? Now we need to calculate radiosity of the surface. It means capital J of the surface. Okay. Second, net radiative heat transfer. So here, what is Q net? Net radiative heat transfer, it means it is J minus G. J means total electromagnetic wave which is emitted by the surface, and G means total electromagnetic wave which is received by the surface. So net heat transfer means J minus G. Okay. Now, and the third one is calculate above quantity surface if the surface is considered to be black body. Okay, done. So now first, here in the question, alpha absorptivity is given as 0.8, temperature is 100 degrees Celsius, Ng irradiation is 1000 watt per meter square, and area is 0.1 meter square. So first we need to find out the radiosity. So as we know, as we have just discussed, there is radiosity is nothing but total emission. First, because of its own temperature, which is body's emissive power, capital E, plus amount of irradiation which is going to be reflected by the body. The total amount of electromagnetic wave which is incident on surface is its G, and from that amount, based on the reflectivity of the body, some amount will be reflected back. So it is depends on the reflectivity. So rho into G is going to be reflected. So combination of rho into G plus emissive power, electromagnetic wave emitted because of its own temperature, this combination, total electromagnetic wave emitted, is known as the radiosity, which is capital J. Now we know emissivity epsilon is equal to E by EB, emissive power of body divided by emissive power of black body. It's give us a epsilon emissivity. So capital E can be replaced by epsilon into EB because of that equation, plus rho into G as it is. Now from the Kirchhoff's law, we can replace this emissivity by the absorptivity. So replacing emissivity epsilon by absorptivity alpha. Now from the Stephen-Boltzmann law, EB is equal to sigma into T raised to 4. So instead of EB, I can write sigma into T raised to 4 plus rho into G as it is. Done. Now for any body, absorptivity plus reflectivity plus transmittivity is equal to 1. This body is opaque surface, so transmittivity is equal to 0. Tau is equal to 0. So rho is equal to 1 minus alpha. And here value of alpha is 0.8, so rho is equal to 0.2. So putting the value of rho as 0.2, value of G is 1000 watt per meter square, alpha is 0.8, sigma is 5.67 into 10 raised to minus 8, temperature is 100 degrees Celsius plus 273 for converting it into Kelvin. So by calculating this value, we will get value of radiosity, J is equal to 1078.02 watt per meter square. Now second, net radiative heat transfer. So for net radiative heat transfer, for equation would be Q net per unit area, so divided by A, J minus G. If area is given to you, so in this question area is 0.1 meter square, so we need to just cross multiply this area with J minus G. We have value of J, we have value of G, area is 0.1, so net radiative heat transfer is 7.8 watt. Now we have to calculate again these two, first and second point, by considering this body as a black body, not as a gray body. So if we consider this body as a black body, then again if we calculate radiosity, so for black body we know there is a transmittivity is equal to 0, reflectivity is equal to 0 because black body absorbs every electromagnetic wave incident on its surface, so alpha is equal to 1, absorptivity is equal to 1. So if we put rho is equal to 0 in this equation, then this whole term will become 0. Then J is equal to E. E means black body emissive power. We know the value of black body emissive power is sigma into T raised to 4. So for sigma T raised to 4, value of sigma is 5.67 into 10 raised to minus 8. Temperature is 373 Kelvin. So for black body, radiosity would be 1097.54 watt per meter square. Clear? And net radiative heat transfer, A, J minus G, we know value of area 0.1, J is 1097.54 minus value of G is 1000. So Q net would be 9.75 watt. Clear? So that's it for today. Thank you so much.